this is the first video in AP Calculus over related rates, which is section 4.6 in your textbook. So it's basically where we're going to look at derivatives of related variables and how the rates of change of those variables affect the rates of change of each other. So related variables are two or more related variables that are all changing with respect to time. All the derivatives that we've done up to this point have all been derivatives with respect to x. So even back when we were doing implicit differentiation and we would take a derivative of a y variable, we would have to write dy dx next to it to basically convert it to a derivative with respect to x, even though it was the letter y that we were working with. For this stuff, though, when you're talking about a rate of change, really and truly the only independent variable in the whole world is really time. So even the x variable changes with respect to time. So really related rates are just implicit differentiation, but everything is going to have to be converted to a derivative with respect to time. So for example, here I have just a simple equation y equals 2x. If I take the derivative of that, well, the derivative of y is 1, but I need to convert it to be with respect to time. So it would be 1 dy dt. And then the derivative of 2x, traditionally we would write 2. But to convert it to be with respect to time, we would write dx dt next to it. And then in a situation like this, maybe they would give you the rate of change of the x variable and ask you to then find the rate of change of the y variable. So it would simply just be a matter of substitution. So speaking of, we're going to look at another just algebraic use of related rates. So this says when x is equal to 1, dx dt is equal to 3. Find dy dt when x equals 1 if y equals x cubed plus 2. So we're going to start with that equation that they gave us, y equals x cubed plus 2. If I just go through and straight take the derivative of it, the derivative of y would be 1, but then I would write dy dt. Then the derivative of x cubed would be 3x squared, but I'm going to write dx dt next to it. And then the derivative of 2 is 0, so it goes away. So now they're wanting us to find dy dt. So it's okay that we don't have a value for it. But in order to find dy dt, I need to be able to substitute a value for x and substitute a value for dx dt. So they told us that when x is 1, dx dt is 3. So really it's just a matter of substitution of the correct values in the correct places. So 3 times 1 squared times 3 would be 9. So what that means is that at the exact moment when the x-coordinate is 1 and the x-coordinate is changing at a rate of 3, then the y-coordinate would be changing at a rate of 9. But all three of those things are related. If I change the x variable or if I change the rate of change of the x variable, that's going to affect dy dt as well because they are all related. All right, now let's look at a geometry relationship. It says assume that the radius r of a sphere is a differentiable function of t and let v be the volume of the sphere. Find an equation that relates dv dt and dr dt. So this is kind of like the optimization. If I want to find a way to connect dv dt and dr dt together, then I really need to find an equation to begin with that connects v to r, hopefully. So they're talking about a sphere. You may or may not remember, but the formula for the volume of a sphere, you would need to look it up if you didn't remember it and you were having to do one of these problems, is v equals 4/3 pi r cubed. So now to relate dv dt to dr dt, I'm going to take the derivative of this entire equation. So the derivative of v is dv dt. And then over here on the right-hand side, pi is a constant, so it's going to represent like a coefficient, just like the 4/3. So power rule, I would bring the 3 in front. 3 times 4/3 is just 4 times pi. Now the r is squared. And then I would write dr dt next to it. So that's the relationship between the rate of change of r and the rate of change of v. So the next slide here is essentially just the strategy for solving related rates problems. It's very similar to the strategy for solving the optimization problems we've been doing. You need to understand the problem. That may, mostly it's just reading through the problem perhaps multiple times, pulling out what variables you need to be working at, with and any values that you have, and specifically what rate of change it is that you're looking for. Then you want to develop a mathematical model. Most of the time that will involve drawing a picture, especially if it's a geometric situation, labeling important parts. Step 3 is then writing an equation to relate the variables whose rates of change you're looking for to the variables with the rates of change that you know. The only difference here with related rates is a lot of times related rates problems, we can get through a whole problem just using one equation, whereas you've noticed with the optimization problems, a lot of times we've had 2 or even more equations going on in one problem. And then 4, we differentiate the equation completely with respect to time, substitute what we know, solve for what we don't know, and then step 6 would be to interpret your solution and ideally to write it as a complete sentence. So the most important thing I can tell you though, oh, it must be on the other side, is do not substitute any numbers into any of the equations you create until after you have taken the derivative. Don't put any numbers in for values. If they tell you the radius is this or x is this or whatever, do not substitute those values in until after you've taken the derivative. That's very, very important. It will mess up your whole derivative if you substitute numbers before differentiating. So here's another geometric situation. It says a pebble is dropped into a calm pool of water, causing ripples in the form of concentric circles. And you've got a little picture of the example shown over there on the right. So concentric circles are just circles that share a center. The radius of the outer ripple is increasing at a constant rate of 2 feet per second. When the radius is 3 feet, at what rate is the total area of the disturbed water changing? Okay, so the first thing I'm going to notice is what are they asking me for? The rate of the total area. So that tells me I need an area formula so that then I can take a derivative of that letter A. So circles, hopefully you remember the formula for area of a circle is pi r squared. Luckily, all the other information in this problem pertains to the radius of the circle. It is changing at a rate of 2 feet per second. So that is dr dt is 2 feet per second. And the circle is growing, so that would be a positive 2. If the circle was shrinking, then that rate would be a negative 2. And then it says when the radius is 3 feet. So r is 3 feet. Hopefully that will be all the information I need to then find dA dt. So I'm going to take the derivative of the equation I created. Derivative of A would be dA dt. The derivative of pi r squared, remember pi is a constant, so we treat it like a coefficient. Do the power rule, we get 2 pi r dr dt. Then it's just a matter of substitution. The radius is 3, and the rate of change of the radius is 2. So real easy multiplication, you get 12 pi. Now the units, let's think about the units. If you're not sure what the units are, go back to what we're finding the rate of change of. It's dA over dt. So the units are going to be area units divided by time units. So area is always square units. Anything you've ever measured since elementary school when you started finding area was always like inches squared, centimeters squared, whatever. So since we're measuring our radii in feet, the area would be square feet. And our time, we can pull that from the dr dt. Time is being measured in seconds. You will get counted off if you do not use the right units. And you will also get counted off if you do not put units on your answer when you have units in the problem to where you can come up with what the units should be. All right, let's look at another geometry problem. So this time we have air that's being pumped into a spherical balloon, and the radius is changing at a rate of 1.5 inches per minute. And you got a little picture so you can see what's going on. Obviously the balloon is getting bigger. So that rate of change of the radius would be a positive 1.5 inches per minute. Find the rate of change of the surface area. So they're wanting us to find, we'll just call it a capital S, ds dt, when the radius is 6 inches. So I'm given information about the radius. They're asking me questions about the rate of change of the surface area. So I need a formula for the surface area that hopefully includes the letter R for a sphere. So if you need to look it up, look it up. But the formula for surface area of a sphere is 4 pi r squared. So if I take the derivative of that, I get ds dt equals 8 pi r dr dt. Then it's just a matter of substituting my information in. So I've got 8 times pi, r is 6, dr dt is 1.5. So when you multiply that out, 8 times 6 times 1.5, you get 72 pi. And then our units, the radius was being measured in inches, so the surface area would be square inches. And the rate of change for the radius was in per minute, so that will also be the time for the rate of change of the area. All right, so those are some good geometry examples. But now let's take it in a different direction with our applications of derivatives. So here we're going to talk about money. So the company's profit P in dollars from selling X units of a product can be modeled by P equals 200X minus 1/2 X squared. The sales are increasing at a rate of 10 units per day. Find the rate of change in the profit, and they even gave you the units, when 50 units have been sold. Okay, so let's go back through it again. A company's profit P from selling X units can be modeled by. So I have my function. So I'm not even going to have to come up with a function this time. They've already given me the function. Let's see what else they've given me. The sales are increasing at the rate of 10 units per day. So that would be the rate of change of X. dx dt is 10 units per day. Find the rate of change in the profit, so that's dp dt. So that's what they're wanting us to find when 50 units have been sold, so when X is 50. Okay, so back over here in the equation that they gave me, I'm just going to go straight through and take the derivative. dp dt equals the derivative of 200x would be 200 dx dt, and the derivative of 1/2 x squared would be x dx dt, and then we substitute. So 200 times 10 minus 50 times 10, that becomes 2,000 minus 500, so we get 1,500. And the unit, since we're talking about profit, is in dollars, and time is being measured in days. So $1,500 a day. I'm going to end the video there. I am going to make a second video with a few more examples if you would like to watch those as well.